Wojtek, you can start.
Okay, so I hope you see my slides.
Yeah, everything is fine. Yeah.
Okay. Okay, so hello everybody. I'm Wojtek. Thanks for introduction. And today I will be speaking about a paper approximating pathwidth for graphs of small treewidth. And this is joint work with Carla Grenland, Gwen Joret, and Bartosz Walczak. Okay, so we'll start with motivation and results description. So I hope that you are familiar with polynomial excluded grid minor theorem, which states that there is a polynomial relation between treewidth of a graph G and the biggest grid minor that it contains. Yeah, this is a result of a type that class of graphs with small treewidth is kind of the same as class of graphs that have no big minors, grid minors. And another result of this type regards tree depth. If you don't know what tree depth is, I will not define it because it's not that important for this presentation, but there is another result stating that if tree depth of a graph is sufficiently big, then it either has a big treewidth or contains a big binary tree as a minor, or it contains a long path. So for treewidth, you can think of a grid as like a canonical obstacle. And for small tree depth, you can think of three kinds of different canonical obstacles, being big grids, big binary trees, and big paths. Okay, but what about pathwidth? Can we do something similar? And the answer is yes. And first result that we prove is that if pathwidth has, if a graph has pathwidth at least th plus 2, then it either has a big treewidth, at least t, or it contains a big binary tree as a minor of height h plus 1. So for pathwidth, we can think that there are two canonical obstacles. One is big grids, and one is big binary trees. Yes, so it's kind of in between treewidth and tree depth in that meaning. Okay, and this theorem will be in fact a key insight to approximation algorithm that we will design. This approximation algorithm, when given a graph G and its tree decomposition of width t, outputs in polynomial time an integer 8 h and a path with decomposition of width t plus 1 times h plus 1, and a certificate that path width is at least h. Yes, so it outputs in fact a pretty good path with decomposition and a certificate, and the certificate that this path with decomposition is not that bad. And above theorem connected with a well-known square root of log treewidth approximation for treewidth results in a treewidth times logarithm of treewidth approximation for pathwidth. And since treewidth is not bigger than pathwidth, it can be thought of as pathwidth times logarithm pathwidth, a square root of logarithm pathwidth approximation for pathwidth, which is a polynomial in pathwidth. And the proof of this excluded minor characterization theorem will be simple. So I hope that I hope to explain it fully within this talk. and algorithm will be more complex. So I will try to explain like a rough sketch of it, but I will not go into details. Okay, so I mentioned in the description of our approximation algorithm, I mentioned these certificates for big pathwidth. However, they will already be crucial for proving this excluded minor theorem as well. So I will introduce them now. And we'll define a sequence of classes of graphs. And T0 will be just class of connected graphs. And TH plus 1 will be a class of connected graphs G that contain three pairwise disjoint sets of vertices V1, V2, and V3, such that graphs induced on them already belong to the previous class, to TH, and any two of them can be connected in G by a path avoiding the third one. So I hope you see, yeah, this is like an example, and these paths do not need to be disjoint from themselves. They can intersect each other, but yeah, what we care about is that they avoid the third vertex set. And we would like to prove a few properties of graphs that are contained in these TH classes. And the first property that we would like to prove is that if a graph belongs to TH, then it contains a binary tree of height H as a minor. And in order to prove that, we're going to strengthen this statement a little bit. We want to prove that for each vertex u in this graph, we can find such binary tree, big binary tree, where u belongs to branch set of its root. And in other words, it means that u is either like a root of this minor, or there is a path from u to this root of this minor. Yeah. So.
But so, excuse me, but we're talking a complete binary tree?
Yes, exactly. Yeah, complete binary tree. Okay, thanks for this comment. Okay, so I want to find a path from you to like this interesting part of this graph G, which is like either V1, V2, or V3, or any of these paths connecting them. And cases where this path from you meets one of these sets, and case when it meets these paths are a little bit different, but for simplicity, let's assume that we can find the path from you to one of these sets. Yeah. Yes, that doesn't enter other sets and paths before that. And thanks to paths between these sets, we can find two paths, one from U to set V2 and one from U to V3, that have a common prefix. Yeah, and this path like enters V1, and then one of them goes to one end of path between V1 and V2. One of these paths go to vertex that's an end beginning of a path between V1 and V3, and they enter V2 and V3 in vertices U2 and U3. And thanks to my induction assumption, for vertices U2 and U3, I can find these green complete binary trees of height h-1 within V2 and V3. where there are paths from U2 to root of this U2 to R2, which is root of this binary tree in V2, and from U3 to R3. And altogether, we can see that we see a binary tree that is one level bigger than this green binary trees rooted at R, and there is a path from U to R. So we are done with proof of this lemma. Okay, and next property that you would like to prove about these certificates is that graphs that belong to TH have a big pathwidth. Actually, having big complete binary trees as minors already ensures that pathwidth is at least h/2, but we can achieve a better bound with a very similar proof to the proof that binary trees have big pathwidth. Namely, specifically, we want to prove that if graph belongs to TH, then its pathwidth is at least h. And and we're going to do that by induction as well. So we know that graphs induced on V1, V2, and V3 belong to TH-1, hence their pathwidths are at least h-1. And by contradiction, assume that we can find pathwidth decomposition of G with h-1, which means that bugs in it are of size at least h. And in order to have any chance, pathwidths of V1 vertex graphs induced on V1, V2, and V3 need to have pathwidth at least exactly h-1. And we also know that there need to be bugs bi that have sizes exactly h, and that they are fully contained within corresponding set vi. And without loss of generality, we can assume that this bug B2 is between bugs B1 and B3 in this hypothetical pathwidth decomposition of width H for whole graph G. However, if we remove a bug from pathwidth decomposition, we know that vertices, if we remove vertices of this bug from our graph G, then we know that vertices that are fully contained on the left and vertices that are fully contained on the right are disconnected from each other. However, we know that V1 and V3 induce connected graphs, and there is a path avoiding V2. So actually, there is a path between vertices from B1 and vertices from B3, which is a contradiction. Hence, this pathwidth decomposition needs to be at least of one vertex bigger. Okay. Yeah, and we'll, for these certificates in our approximation algorithm, will it is actually easy to store them. I mean, if you want to prove that a graph belongs to TH, then you want to point out 3 vertex sets that belong to TH-1, and like recursively prove that recursive certificates that they belong to TH-1 as well. Okay, so now we'll try to prove that excludes minor characterization theorem. So if we reformulate slightly our original theorem, it says that every graph with treewidth t minus 1 has pathwidth, has either small pathwidth or contains a big complete binary tree as a minor. And we'll strengthen it a bit by replacing outcome that it contains a big binary tree by the outcome that it belongs to th plus 1. And we already know that if it belongs to th plus 1, it contains a minor of big complete binary tree. Yeah, so theorem 2 implies theorem 1, and we'll focus on proving theorem 2. Okay. However, before doing that, we'll prove an auxiliary lemma, which I will call combining lemma. And it says that if we are given a tree decomposition and a path in it, which is on this picture depicted as B1, B2, B3, B4, and if we consider removing all vertices from this box and from our graph G and look at pathwidth of what remained, if this pathwidth is at most P, then pathwidth of whole graph G is at most P plus T. And it's actually pretty easy lemma. Why is that so?
Sorry, excuse me, can we just repeat the lemma once more?
If I have a path of bugs in my tree decomposition, and from my graph G, I remove vertices that belong to them, if what remained has pathwidth at most P, then original graph has pathwidth at most P plus T.
Okay, thanks.
Okay, and how do we prove that? We prove that by picture. So each connected component of what remained after removing vertices from this box consists of vertices that are like fully within one subtree of this tree decomposition after removing vertices belonging to corresponding to this box. And yes, so you have, let's say, one subtree T1 and that is attached to bug B1. And we know that we can find a path of decomposition of T1 of with at most P plus 1. Yeah, and we'll look at these subtrees from left to right, and we'll concatenate their path with decompositions in that order. So path with decomposition of T1, T2, T3, and then T4. And for the part where we have path with decomposition of T1, to each bug of it, we want to add all vertices from a bug B1, from bug B1. And for T2 and T3, their bug, like parent bug is B2. So we'll add vertices from bug B2 to each bug from path with decomposition of both T2 and T3. And similarly for B4 and T4. And B3 has no like children subtree, but we still want to have it in our decomposition. So we create a path with a decomposition like this, where like each bug in it is formed by taking one bug from path with decomposition of some Ti and adding a whole bug B that corresponds to that subtree. And it is easily seen that this feasible path decomposition, and it has path with at most P plus T. Okay. So now we are ready to prove our theorem And we'll do this by induction on H. And yeah, so we'll start with base, which is H equals to 0. And in that case, if G contains a cycle or a vertex of degree at least 3, then G belongs to T1. And why is that so? Let's consider a vertex of degree 3 and at least 3, and take three arbitrary 3 neighbors. It's 3 neighbors. Okay, and each of these vertices, yeah, it's a connected graph. It means it belongs to T0, and any pair of them can be connected by a path that goes through that vertex that we started with of degree 3. And clearly it avoids the third vertex, the third neighbor. So in that case, such graph belongs to T1. And in the case where G contains a cycle, we can take as these 3 vertex sets any 3 vertices on it. And for each pair of them, there is like 1/2 of the cycle that connects them contains the third vertex, and 1/2 doesn't. So we can see that any pair of them can be connected by a path avoiding the third one as well. So in that case, G belongs to T1 as well. And otherwise, if G doesn't contain any cycle or a vertex of degree at least 3, it has to be a path. And in that case, its pathwidth is at most 1, which is what we wanted to prove. Either G belongs to T1 or it has small pathwidth. Okay, so now we want to prove induction step. So assume that it works for H minus 1. And let us take a tree decomposition T of with T minus 1. And let's consider a first case where there exists a vertex in this tree decomposition such that if we remove from our graph vertices from this bag, then no component of what remained belongs to TH. So we think of components that do not belong to TH as, let's say, small components. There is a vertex in a tree decomposition that after removing them, all components are small. And it means that all components have small pathwidth. And at most, T times H minus 1 plus 1. And what we want to do in that case is to take this pathwidth decomposition, of all these components, concatenate them, and add this back BQ to all of them. What we are doing is actually using combining lemma, where this path, like this backbone in combining lemma, is a single back. Yeah, it's easily seen that it's a valid path with the composition, and it's sufficiently small as well. Okay, so let's consider the second case where after removing for each vertex of our tree decomposition, after removing it, there is a big component in the rest of the graph. And specifically, if you look at this picture, it kind of serves as a definition of gxy that I use in the description of this case. Gxy is a graph induced on vertices that are fully contained within a subtree of x. Like if we are given an edge yx, and we look at the vertices that are contained only in the right part of the tree decomposition, we call that graph gxy. Yeah. So correct description of this case is that for each vertex y, it has a neighbor x such that the graph on in that part is big. It belongs to th. So now, for each such event, for each such hyx, we want to direct it. Sorry, we do not want to direct this edge. We want to consider a set of directed edges that point towards these big subgraphs. In particular, an edge can be directed in both directions if it is the case that both parts on left and on right are big. And our assumption tells us that for each vertex y, there is an outgoing edge from it. In particular, it means that there are at least as many directed edges as there are vertices in our tree decomposition. So it means that there exists an edge that is directed in both ways. Okay. And another property of these directed edges that you want to prove is that if we have edge y, z, that's like directed from y to z, and we have another edge from xy, this edge xy has to be directed towards y as well, right? Because if we know that on the right of vertex z, we have a big subgraph, then on the right of vertex y, we have big subgraph as well, because it contains that big subgraph on the right of z. In particular, it implies that a set of edges that are directed in both ways is connected. Yes. So that's we know that this set is not empty and it's connected. So yeah, let's say it's a subtree of our original tree decomposition. And we want to consider a set of its leaves that will be called Z. And we have two cases. In first case, this set has two leaves, or in other words, a set of edges that are directed in both ways is a path. And each component, like if we remove that, look at other parts of this graph, the edges are, each edge is directed towards this path. In particular, it means that components like T1, T2, T3, and T4 are all small. By small, I mean that they do not belong to TH. And because of that, we know that their pathwidth is small. And because of that, we are done by combining lemma and getting a path with the composition that is not big. And let's consider second case, where this subtree induced by these edges directed in both ways is like more complicated. It's not a path. In that case, yeah, it has at least 3 leaves, and we look at these three leaves that are Z1, Z2, and Z3, and they have big subgraphs G, Z1, X1, and so on. And now we want to prove that so we already have 3 big subgraphs, and what you need to do right now is to find paths between them. For each pair of them, we want to find a path omitting the third subtree. And if we do so, it will be a proper witness, proper certificate that that our graph G belongs to TH plus 1, like this class of 1 level bigger. Okay, And at this point, we want to additionally require from our tree decomposition that it has a nice property that if we cut one edge of it, like the vertices that are fully on one side or fully on the other side, they induce connected graphs. And that is a property that can easily be satisfied. And if we are if from the very beginning we operate on such tree decomposition, then we know that after removing, let's say, G, Z1, X1, the remaining graph is connected. In particular, it means that there is a path connecting like this second subtree with third subtree that omits, that avoids the first subtree, which means that if we do similar argument for second subtree and for first subtree, it means that we have found a certificate that that our graph G belongs to th plus 1, which is the second possible outcome. So in first outcome we produced a small path of decomposition. In second case we produced a better certificate, which is what we wanted to prove. Yeah, so that concludes proof of this theorem. Okay, and now we want to talk about approximation.
May I have one question?
Okay.
I just wanted to make sure that I understand. When you say that an edge is directed towards somewhere, you want to say that there is a smaller certificate in the graph without the adhesion. So the adhesion of the edge is removed when you are looking at the.
Yes.
Okay.
Adhesion is removed.
Okay, so it's beyond the separator. Okay, good. I just wanted to make clear that I understand correctly. Thanks.
Okay, so in our algorithm, we want to prove, like, our algorithm is given tree decomposition of with at most t minus 1, and we want to compute first for three things. First, a number h such that G belongs to th, and pathwidth of G is at most th plus 1. And by our theorem that we have just proved, we know that such number h exists. Second thing that we want to prove is a certificate that G belongs to th. And third thing is this small path decomposition. Okay, and a corollary that I mentioned before as well is that if we connect this theorem with well-known approximation for treewidth, we get approximation for pathwidth. Yeah, and this path decomposition is of width t square root of log t times p, or in other words, it's a t square root of log t approximation of pathwidth. Okay, and we'll do this by bottom-up dynamic programming over tree decomposition. So a few definitions. For x, which is a node of tree decomposition, let Vx be the set of vertices contained only in bags that are descendants of x. Or relating that to what we have discussed earlier, it's like a set of vertices, let's say Gx and parent of x. Yes, and let k be the maximum value of h for x different than root. So we have computed everything that we wanted for like smaller subtrees of our tree decomposition, and k is the biggest value of h that we have found there. Yes, and there are two outcomes of our algorithm. Either we find a way to compute a path with decomposition of widths the same as the biggest width that we have encountered in our children. Yeah, in this case, we need to care to find a good path with decomposition. And in other case, when we are unable to do that, we want to provide a reason why we weren't able to find a good path with decomposition. And that reason is a bigger witness. We set h to k plus 1, and we want to provide a tk plus 1 witness. And in that case, a path with decomposition is actually very easy to find because it can be bigger by t than what we needed in our children. So we can just remove, use combining lemma, where again, when this path, the backbone in combining lemma is a single root back. If we remove that root back and concatenate the path with the composition of our children and add this back to all backs in this path with the composition, it's a good path with the composition, and it's not too big. Like, it's bigger, but we are allowed because we find a better witness. Okay. Yeah. So what we want to look at right now is set z. That will be set of minimal nodes z, such that h of z is k. So on this picture, these are these bugs: bz1, bz2, z3, and z4. Yeah, of course, their ancestors have h equal to k as well. However, if we have like a branch, yeah, that branches to the side, we know that h on this path is smaller than k. These 4 bugs are the only, like, the 4 minimal nodes which cause that h of z is k. Yes, and under these bugs, yeah, we have some subtrees. Yeah, like vz1, vz2, vz3, and vz4. These are vertices that are contained only in bugs, in subtrees and under these bugs. And we want to define a set U, which is everything except these sets of vertices. Okay, so we think of these subgraphs as these big subgraphs. These obstacles why path width is not small. And if you want to find a witness, good witness, we want to find 3 big subgraphs and appropriate connections between them. And that's why we want to consider an auxiliary graph on elements of Z, where there is an edge in this subgraph between Zi and Zj, if there exists a U path connecting Vzi and Vzj. U path is a path with its internal vertices within U. And that condition basically means that we are able to connect a big subgraph corresponding to Zi and big subgraph corresponding to Zj with a path that avoids other big subgraphs. And again, as similarly as in the case of base step of our induction, if this auxiliary graph on big subgraphs has a cycle or a vertex of degree at least 3, then we are able to find a good witness. We have found many connections between, connections between big subgraphs that allow us to say that G belongs to tk plus 1. Okay, so in that case, we are done. And otherwise, this auxiliary graph has to be a path. And actually, there's one more thing worth mentioning, that this graph H is connected because G is connected. Okay. Okay. So now we are in a case where these connections between big subgraphs form a path. So let's think, what are the kinds of vertices that appear in our graph? So here this BZ1, VZ1, BZ2, VZ2, and so on are big subgraphs. And if you have a vertex that doesn't belong to any of these big subgraphs, if there are paths from this vertex within U to 3 different big subgraphs, this will actually create a triangle in that auxiliary graph, which means that each vertex is connected to at most 2 big subgraphs. Yeah, and if it is connected to 2, then there is it corresponds to an edge in this auxiliary graph. This is why vertices that can be connected to 2 various big subgraphs can be partitioned to sets like U1, 2, which is a set of vertices that can be connected to BZ1 and BZ2, U2, 3, U3, 4, and so on. And there are also vertices that can be connected to only 1 big subgraph. So for second big subgraph, it will be U2. For third, it will be U3. And for first and last back, we have, let's say, little exception. We can call this set U01 is actually a set of vertices that can be connected only to the first big subgraph, but for some reasons, instead of saying it's like U2 or U3, we claim it's more like this sets I plus 1. But I will not explain in details why. Okay, and this is like a let's say base for our combining.
So
okay.
excuse me, can I just ask something? What is this BR? Where is it in the tree? Is it like a complete root of everything?
BR, yeah, BR is a root back.
Okay, so it's a root of the entire decomposition somehow.
Yes, exactly.
Okay.
Okay, yes. So continuing, we want to use that partitioning, understanding that structure to hypothetically using combining lemma in the future. However, to use combining lemma, we want to find a sequence of sets, a sequence of bugs. And in order to do that, we'll traverse our tree along this red path. So we start from root bug. We take sequence of bugs from this root bug to BZ1, then take BZ1, then take a look at sequence of bugs from BZ1 to BZ2, and from BZ2 to BZ3, and BZ4, and coming back to root bug. This is some sequence of bugs. However, one problem with it is that like one bug can appear multiple times in it. And it could hypothetically be the case that one vertex like doesn't appear at a consecutive interval of these bugs. However, when we are traversing that path, we are actually interested in the path, in the intersection of what is in these bags, and the interesting part on this picture above. For example, when traversing, when looking at bugs on the path between BZ1 and BZ2, that part of this red path on this picture above, it goes through U12. It means that when traversing that path, we intersect these bugs with set U12. We don't care about vertices other than U12 when creating that sequence. Yeah. So on the first segment of this path, we care about vertices that can be connected to BZ1 with like this set U01. Then we take whole bag BZ2. Then this path between BZ1, BZ2, but intersected with vertices from U12, and so on. Okay, and what we aim to do is we want to remove, like we want to use that sequence of bugs as properly restricted as this backbone for our combining lemma. And in order to do that, we need to know that if we remove all these vertices from this backbone, like all other components are small. They do not belong to TK. And this will be our first easy case. If it is indeed the case that all other components, after removing these vertices from this created backbone, do not belong to TK, then we are done by combining lemma. And in other cases, where there is some component belonging to TK, we'll actually use it to provide a better witness. So assume that there is a big component C hidden. Let's say it's hidden within U2. In that case, we want to look at three big subgraphs. One big subgraph is this C. Second big subgraph is a graph induced on VZ1, and a third big subgraph is a subgraph induced on VZ3. And we want to find these green connections between them. It can actually be argued that these green connections exist, and because of that, we are able to find a bigger witness. And there is another case where this big component lies within U12. Because it doesn't necessarily have to be the case that this, when we are traversing the red path and restricting to U12, it is not the case that this will cover a whole set U12. There are some vertices that are from U12 that are not covered by this backbone. And if there is a component within that U12, big component, then we find our witness by connecting it to the previous big subgraph, to the next big subgraph. And we can also find a connection between this VZ1 and VZ2 as well, which form a big witness as well. And it can be shown that these are actually the only cases. So we are done with our rough sketch of this algorithm. However, there are a few caveats that I have swept under the rug when describing it.
But excuse me, sorry for interruptions, but I would really like to understand this. So can we recap the algorithm once again, just the algorithm and not the proofs?
Okay, so we are doing dynamic programming, and yeah, we already computed everything for our descendants. We identify like the biggest descendants. Yeah, we create an auxiliary graph on them. If this is not a path, then we are able to find a better witness, bigger certificate, and getting a path with the composition is easy in that case. And in a case where this auxiliary graph is a path, we cannot allow ourselves to make a bigger path with the composition at this point.
Okay, that's enough for me, by the way. Thanks
Okay.
a lot.
Okay. Anyone has any other questions at this point?
I just wanted to say that we are sort of short of time, so if we could sort of get to wrap up, this would be preferable.
Sorry for interruptions.
No problem. If
fine.
there are any questions, of course, it's our goal to understand it. But
Yeah. But I'm converging towards the end either way. Just wanted to mention a few things that I didn't point out before. Yeah, so first thing is that actually when deleting that backbone, the connected components that we are left with do not have to be like subgraphs that we already computed information about. They can be like kind of weird. And so a priori, if we are using that algorithm, calling that algorithm recursively, there can be exponentially many of them. Yeah. However, after like a proper analysis, it will turn out that there is actually a polynomial number of them, but this is a complex argument. Yeah. Second thing is that if you remember a proof of our excluded minor characterization theorem, we needed to have a like connectedness property of our tree decomposition, and we need it here as well. And when restricting to subgraphs, it can be the case that we need to modify this tree decomposition, even though it could have our property at the beginning. After restricting, it could lose it. So in order to deal with it, we need to consider like an elegant kind of tree decomposition. Yeah, but that's another topic as well. But we are able to find them in such a way that will behave properly when restricting to subgraph. Another thing is that we need to have another parameter as an input of our procedure, which is an upper bound request. It means that we are given some additional parameter b, and when this age of this graph is at least b, we actually do not care about path with decomposition. In that case, we are only interested in getting big witness. Or in getting an information that path width is small. Yeah, but it's not crucial to understand the algorithm, so I omitted it. Yeah, and we need to heavily use the memorization as well to not repeat these recursive calls for subgraphs that we already computed information about. Yeah, so actually the complexity analysis of this algorithm is pretty complicated. It is highly non-trivial why it runs in polynomial time, but it does. And this polynomial is actually pretty good. Not sure what exactly it is, but I think something probably like n squared log n, something like this. Okay. And something that I will discuss very briefly is tightness. So I basically would like to prove that our exclude minor characterization theorem was tight, and we want to prove we want to prove that we can shave off at most multiplicative factor, and there is some log of t lingering for technical reasons, but basically the example that that we want to show is a blow up of a big ternary tree, where each vertex is blown up to a clique, and each edge is blown up to an arbitrary matching. And such graph has treewidth t, has a big pathwidth, and because of volume argument, there is no big binary tree. Yeah, so small tree, small binary tree, but reasonably big pathwidth. Yes, okay, and that's basically everything I wanted to say. So thank you for attention.
Yeah, thank you very much. Maybe on 3, 2, 1 we can unmute ourselves and clap. So 3, 2, 1. Good. Are there any questions at this point?
Yes.
Okay, yes.
Sorry. Okay, that's my last question, I promise. So are there any other approximations for pathwidth than with treewidth, like anything else, or is it the only approximation algorithm for pathwidth?
There is an approximation, log n approximation, that is actually like an approximation for tree depth as well, where we compute like tree depth decomposition of treewidth decomposition, which gives us like an approximation for tree depth that can be transformed to a pathwidth decomposition. And there is also a pretty slow algorithm for computing exact path decomposition, and by a trade-off trick between these two things, this log n approximation and this slow exponential algorithm, it is possible to get a polynomial approximation for pathwidth, but it will be of order pathwidth cubed, if I'm not mistaken.
Right. Are there any other questions? Okay, doesn't seem so. So I think that we can thank Wojciech again. I'm stopping the recording at this point.